I am Anil Kumar. Welcome to my series on inverse trigonometric functions. In this video, we are going to discuss some properties of inverse trigonometric functions and take up questions related to that. You can always visit my website globalmathinstitute.com for the new videos being uploaded. You can always contact me on the email address given to learn directly from me. We are conducting one-on-one Zoom classes. In this video, we are going to see how do we solve questions related to equivalent inverse functions, how do we evaluate composite inverse functions, how do we simplify expressions with inverse. We'll also explore some trigonometric identities and take related applications, and then we are going to solve equations. So this is a simple trigonometric relation, kind of Pythagorean equivalent. Secant square theta equals to 1 plus tan square theta, cosecant square theta equals to 1 plus cot square theta, which we are going to use in this video. In the next video, we are going to take all compound angles and half or double angle. Now, we'll consider how the angle A is related with sine inverse, cos inverse, tangent inverse, cosecant inverse, secant inverse, and cotangent inverse. As you can see, this angle A can be defined in terms of all these trigonometric ratios. They must be equivalent, correct? And that helps us to solve many questions. We're going to explore that now. Let us first understand this angle A itself. So let's take this right angle triangle ABC. In that case, sine of A is opposite side over the hypotenuse, which is A over C. That clearly means that angle A will be sine inverse of A over C. Well, cos A is adjacent over hypotenuse, that is B over C. That means that A should be cos inverse of B over C. Likewise, tan A is opposite over adjacent, that is A over B. Angle A is tan inverse A over B. That means we have defined this angle A in three different ways. Well, you can also define in terms of cosecant, secant, and cotangent as shown here. Well, angle A is same, right? Therefore, all these inverse functions are equivalent. That is what we are trying to say here, equivalent inverse functions. Now, this is extremely important property, as you will see in the following examples, how it helps to simplify expressions. Let's take our example number one, which is, well, there are many parts to this, so six of them. I will do three of them, right? A is cos of sine inverse 3 over 5. Let us try to think about it. You can actually pause the video at this stage. There are six parts, solve them, and then look into my solutions. I'm providing solutions for only three of them. The other three should follow the same path. Correct. Now we have cos of sine inverse 3 over 5. We know one thing, that is the property. Cos of cos inverse x is x, sine of sine inverse x is x, tan of tan inverse x is x. Correct. In their restricted domains, perfect. Now, since we are talking about these triangles, we'll think that we are working in quadrant 1 from 0 to pi by 2. So all those domains are restricted, and they all have this 0 to pi by 2 as a common domain. So let's consider that to solve these questions. Okay, cos of sine inverse 3 over 5. What I can do here is I can make my triangle. So let us say that 3 over 5 is the two sides, the opposite and the hypotenuse, to define sine inverse of 5. That means adjacent should be what? Well, applying the Pythagorean theorem, that should be 5 square minus 3 square square root. And that clearly, as you know, is 4. Correct. 3, 4, 5 is the simplest right angle triangle which we know about. Clearly, we can now write, here is the solution. Let's look into the solution. Cos of sine inverse 3 over 5. Correct. The idea is to write this angle A in terms of cosine. So if you look into it, cosine is the ratio of adjacent over hypotenuse. So sine inverse 3 over 5 is actually equivalent to cos inverse 4 over 5, correct? Cos inverse 4 over 5. And therefore, we can write it. And so we get cos of cos inverse 4 over 5 that relates to 4 over 5 as our answer. Clear? So that is the strategy. Let's take one more. Cosecant sine inverse 3 over 5. So in this particular diagram, what is the cosecant function? Well, the cosecant function is 5 over 3, right? 5 over 3. So cosecant sine inverse 3 over 5. Sine inverse 3 over 5 can be written as cosecant inverse 5 over 3. Now we have cosecant of cosecant inverse. We get that same value, which is 5 over 3 as our answer. Correct? Now, I would like you to solve these three questions and then look into the fourth solution. Here we have tan and cosecant inverse 5 over 4. Well, that means, think like this. We are given 5 and 4. We need to find the other side. We find it out. But we need to write this in terms of tan. So, what do we get? Well, tan of cosecant inverse 5 over 4 is as good as tan of tan inverse 4 over 3. We're looking now from the angle B side. You get the idea, right? So, angle B side. When we say cosecant is 5 over 4, right? In that case, the opposite to B is 4, right? You see that? So, we are looking from angle B. So, tan inverse should be 4 over 3. And therefore, tan of tan inverse will be 4 over 3 as shown here. So, I hope the concept is clear. You can clearly now write equivalent inverse trigonometric functions, correct? Let's take up example number 2 now, which is, now we are giving you values. Perfect. Cos of sine inverse 15 over 17. Once again, instead of our 3, 4, 5 triangle, now the triangle which we have is sine inverse 15 over 17. Means we have a triangle which is from angle B 15 over 70, right? So in this case, our focus is angle B from the shown diagram, the opposite side being 15, the hypotenuse being 17. Correct. Now, we have to convert this sine into cosine. Obviously, we'll take adjacent type 8 over 17. So we are writing sine inverse of 15 over 17 as cos inverse of 8 over 17, a cofunction identity, you remember. So cos of cos inverse 8 over 17 is 8 over 17. Got it, right? Now let's take another example, which is example C, which I'm taking here. Secant tan inverse 8 over 15. Same triangle can work for us. We have to write the inside function as a secant function, correct? So from here, we are saying tan inverse 8 over 15. That means now we are really looking into this as the opposite side. So we're talking about angle A now. Earlier we were talking about angle B. So clearly, from angle A side, secant will be what? Secant adjacent side is now 15, will be 17 over 15. So we can replace that with 17 over 15. Secant of secant inverse is the value itself, x. 17 over 15 becomes our answer. Clear. Now here is another very interesting case. We'll take sine of cot inverse 15 over 16. So when you say cot inverse 15 over 16, so the ratio is 15 over 8, sorry, 15 over 8, right? So 15 over 8 means we're now looking from angle A side. Once again, it is cotangent. So from angle A side, the sine is 8 over 17. And therefore, we get sine of sine inverse 8 over 17, giving us the value 8 over 17. Correct? So we have shown you three examples. The other three are for you to explore. Now here is what you're going to learn. Secant of cos inverse x is 1 over x, right? So whenever you do the reverse like this, you may see and check this result, okay? Cosecant of sine inverse x will be 1 over x. Similarly, tan of cotangent x will be 1 over x. So you can actually verify this with some examples. Now let's move forward. Take example 3 now. In this example 3, we are going to evaluate each of the expressions. The three given to you is cos of sine inverse x, cosecant sine inverse x, secant sine inverse x. So we'll actually write an expression for it, right? Not exactly evaluate, but you can say write simplified expression, because they are in terms of x. Now, let us see how do we solve such questions. When we are saying sine inverse x, that means the opposite side has length of x and the hypotenuse is 1. Now you can always find the third side using the Pythagorean theorem, so it is definitely 1 square minus x square square root. Well, we got our triangle now, so we can write this in terms of cos, cosecant, and secant, and that will help us to solve all the three. Rather simplify them, correct? So let's see, how did we do that? So we have sine inverse of x, we want to write in terms of cos. So definitely, to write in terms of cos, we need to find the third side, which is square root of 1 minus x squared. And from the same angle, which is a, cos will be 1 minus x square square root divided by 1, which gives us 1 minus x squared, correct? Okay, so I forgot to write square root here. So let me add square root, sorry. So in this particular case, we'll get cos inverse of square root of 1 minus x squared. So the answer will be square root of 1 minus x squared. So that is what we are going to get as a result of this, correct? Now, let us solve the second one, which is cosecant sine inverse of x. Now, sine inverse of x, we can write this in terms of cosecant as 1 over x, correct? So the inside function becomes cosecant inverse of 1 over x. Now, cosecant of cosecant inverse of 1 over x is 1 over x, correct? So that is what we get. So our answer is, as you can see, the reciprocal of x. This is what we expected. Okay, secant sine inverse x. So if you look into this particular diagram, our triangle itself, to write this as a secant function, we are looking from angle A, the adjacent side is square root 1 minus x squared. So secant inverse 1 over square root 1 minus x squared. So we'll have 1 over square root 1 minus x squared in the denominator. So that becomes the solution for this particular case. Now let's take example 4. It is evaluate each of the following: cos of tan inverse x, cosecant of tan inverse x, secant of tan inverse x. It is kind of similar to the previous example. I would like you to pause the video, answer this question, and then look into my suggestions. Well, we'll again make a right triangle. We're talking about tan inverse of x, correct? So from angle A, to write the tan, we're going to get x over 1, opposite side being x, adjacent being 1. Now that helps us to get the third side, which is the hypotenuse equal to square root of 1 plus x squared. Now we'll see how do we find cos tan inverse x, cosecant tan inverse x, and secant tan inverse x. The idea is to use the properties of equivalent inverse functions. So tan inverse x, how do we write in terms of cos? Well, looking from this particular angle, cos is 1 over square root of 1 plus x squared as mentioned here. So that will be cos inverse of this. And cos of cos inverse will give us the value of the x itself, which is 1 over square root of 1 plus x squared. So I hope the concept is absolutely clear. The next one here is cosecant of tan inverse x. We need to write tan inverse x in terms of cosecant. So again, getting back to our angle A, cosecant will be square root of 1 plus x squared over x, and that becomes the answer in this case. The last, secant tan inverse x, secant is relating the hypotenuse with the adjacent side. Now, hypotenuse divided by 1 will be the hypotenuse itself. So we get square root of 1 plus x squared as our answer. Clear? So that is how we are going to answer such questions. Here is example 5. We need to evaluate composite expressions. So this time we have an expression which has kind of cos of cot inverse sine of tan inverse 1. That is example 1. And B is sine of tan inverse cos of cot inverse square root of 3. Now let us see how do we solve such a question. So let's take part A. The idea is to start with inside out, correct? As we did earlier also. So we'll begin from inside function, which is tan inverse of 1. We know tan inverse of 1 is what? Is pi by 4. So we replace this tan inverse of 1 with pi by 4. Now, what is sine pi by 4? Sine pi by 4 is 1 over square root 2. So we replace that with 1 over square root 2. Now we need to solve for cot inverse of 1 over square root 2. So let's make another triangle. Looking from the angle A itself, 1 over square root 2 means adjacent over the opposite side, and hypotenuse will be square root 2 square plus 1 square, which gives us square root of 3. So we get the hypotenuse, or write our triangle. Since cos is outside, we want the inside function should be cos inverse. So cos inverse is 1 over square root 3. Cos of cos inverse will be 1 over square root 3. You get the idea. That is how we have to solve it. So I hope it is clear. Try to do part B yourself and then look into this suggestion. Start from inside out, cot inverse of square root of 3. So we are looking into this particular triangle. Cot inverse of square root of 3 means that the side will be, well, cot is adjacent over opposite side. So in this case, adjacent is 1 and opposite side is this. So that should be actually, so it is kind of wrong here. It should, let me correct this. Or let me make this as cot inverse of 1 over square root 3. Let me rewrite this. Okay, so let me correct this part. I'll make this question as 1 over square root 3 here. So if I do 1 over square root 3, then we are looking into the adjacent side here and the angle as pi by 3. Clear? So I just made this correction. I wrote this as cot inverse of 1 over square root 3. Okay. So made a change here. Correct? So from the cot point of view, cotangent adjacent over the opposite side. So that becomes angle pi by 3. So we'll replace cot inverse of 1 over square root 3 by pi by 3. So we get cos of pi by 3, correct? Now what is cos of pi by 3? Well, cos of pi by 3 is 1 over 2. So we got this value from pi by 3 cos to 1 by 2. So tan inverse of half. Now to get this solution, we'll create a triangle. Tan inverse of half, 1 over 2, right? So 1 is the opposite side, 2 being the adjacent, square and add them. So you get 2 squares 4, 4 plus 1 is 5. Square root 5 will be the hypotenuse. So we can now write this in terms of sine. Sine inverse of 1 over square root of 5. That gives us the value 1 over square root 5 as our answer. Normally, it is a practice to rationalize. So we'll write this as square root 5 over 5 as our answer. Is that clear to you? Right? So there was a typing error. I kind of changed this question cot inverse 1 over square root 3. So that is a change which has been made here. Okay, let's move forward and see how do we solve similar questions. Here is a variation. We'll again use, now this time we are going to use trigonometric identities to simplify. Evaluate the following expressions. Three of them are secant square tan inverse of 3, cosecant square cot inverse of 2, tan square secant inverse of 3 plus cot square cosecant inverse of 2. So I'm going to use these two identities to simplify the given expressions. As you know, 1 plus tan square theta is secant square theta, right? This equation can be rearranged and written in so many different forms. Cosecant square theta is 1 plus cot square theta. Okay, so the very first one is secant square tan inverse of 3. Now secant square can be written as 1 plus tan square, right? So I wrote 1 plus tan square of the argument, which is tan inverse 3. Now, tan square means we'll square from outside, right? So inside we can write tan of tan inverse 3 whole square. Perfect. Now tan of tan inverse 3 is 3 and we are going to square it. 3 square is 9, 9 plus 1 is 10, and that is how we get our result. Clear? Same strategy. You can apply for B and C, check it out, and then see my solution. So now we'll do cosecant square cot inverse of 2. Now, you know this identity. Cosecant square theta is 1 plus cot square theta. So we wrote this as 1 plus cot square. Inside, the argument is cot square, cot inverse 2. So this square can be taken outside. We can square later, right? So cot of cot inverse 2 whole square. 1 plus, of course. So 1 plus 2 square, 5 is the result. Now let's do part C, which is tan square secant inverse 3 plus cot square cosecant inverse 2. So in this particular case, first I just copied the question. Tan square secant inverse 3. Now, tan square can be written as secant square minus 1, correct? So we can always write tan square theta as secant square theta minus 1, and that is what we did here. Correct? So we replace the first term by secant square secant inverse 3 minus 1. Similarly, the second term cot square cosecant inverse 2 as cosecant square cosecant inverse 2 minus 1. Correct? So we wrote that also. Now, the square of 3 will be the result of the first term minus 1 as such. 2 square, the result of the third term minus 1. 9 minus 1 plus 4 minus 1 gives us 11 as our answer. Clear? So that is how we can actually use these identities and work with inverse functions also. Now we are going to take up the last question, which is how do we solve equations? We'll have to find the value of x. The given equation is sine of cot inverse x plus 1 minus cos of tan inverse x is equal to 0. So that is the equation which we need to solve. So we'll put all our learnings in this particular case and see how do we solve this equation. Now clearly we have, well, this is not there. So we have sine of cot inverse x plus 1 minus cos of tan inverse x equals to 0. So the inside term, which is cot inverse x plus 1, let's work on this. Make your triangle for cot inverse x plus 1. For angle A, x plus 1 becomes the adjacent side, opposite being 1. Hypotenuse clearly will be a square plus b square square root. So when I do a square, what do I get? Let's do this. So let's work this out, right? So we have x plus 1 whole square plus 1, right? Which is square you can write. And that gives you x square plus 2x plus 1, and that clearly is x square plus 2x plus 2, correct? So that is how we get this particular side, hypotenuse. So once we have our triangle, we can now write the inside terms in inverse of any of our trigonometric ratios. Since the outside term is sine, we are going to write it in terms of sine inverse. Now if you look at it, sine inverse would be 1 over the hypotenuse, and that's what we wrote. Similarly, in the next expression, which is cos of tan inverse x, we need to draw another triangle. So here is your triangle for tan inverse x, opposite side being x, adjacent being 1. Hypotenuse will be 1 plus x square root. Now, since outside function is cos, inside should be cos inverse. cos will be adjacent 1 over square root of 1 plus x squared. Now that should be equal to 0. This is the equation which we need to solve. Now, to solve this equation, we know that the inside part is sine inverse, the outside is sine. So what do we get? We get the value of x itself. So x minus, here also, the inside term is what we get because cos of cos inverse x is x, right? So we get 1 over square root of x squared plus 2x plus 2 minus 1 over square root of 1 plus x squared equals to 0. You can multiply by the common denominator, and so you get 1 plus x squared, or rather we'll first square it, right? So first you square. So to square, what you have to do is you take it to the right hand side and then square, right? So that'll be better. Otherwise, there is a problem here, right? So I should rewrite this kind of like this. I missed a step here. So we'll say this could be written as 1 over square root of x squared plus 2x plus 2 equals to 1 over square root of 1 plus x squared, correct? So first you write like this and then square both sides. Once you square, in that case, you can bring them together and simplify as we did here, correct? So, and then you simplify. Correct. So you come to this expression which is 1 plus x squared minus x squared plus 2x minus 2. Correct? You could also multiply each term with the square roots and then later you can square. But this is better. So follow this path and then get to this equation. Now you can see simplify x squared minus x squared, that gets cancelled. So you get minus 2x minus 1 equals to 0, simplifies to x equals to minus half. And so we get the value of x as minus half in this particular case. So that is how it could be solved. So with this, we end our video. I hope you learned the strategies. How do we use the trigonometric identities to simplify? How do we use the inverse of inverse functions to simplify? And how do we solve equations? In the next video, we are going to use compound angle identities to make it more interesting, and then we'll take more examples. Thanks for your time and all the best.